Obtain the mathematical model of system shown in figure. Here, three masses are there. M1, M2, and M3. And finally, obtain the electrical force voltage analogy of given mechanical system. And hence find force voltage analogy of given system. Here, what are the forces acting on M1? Because of K1, because of K2, and FV1, FB1, or simply B1. These are all dashpot coefficient, frictional coefficient. Sometimes they will put like this. That's why I took this out. Because of frictional force, this dashpot effect will be there. That is mentioned as FV1. Here FV2. Between two masses also that is mentioned. They mentioned FV3 and FV4. FV4. The displacement of mass 3 is x3. This is x3. Displacement of mass m1 is x1. So what are the applied force? Applied force is on m2 only, f of t. Now, if you draw the free body diagram for m1, displacement is to its right. F, no force, no applied force. Displacement is x1 to the right. Therefore, reaction forces are acting from right to left because of F, M1, because of K1, because of K2, and because of FV1, of course, because of FV3. These are the 5 reaction forces acting on M1. Fm1 is M1 d square x1 by dt square plus Fk1, one end is fixed, therefore K1 x1 plus K2, both ends are free. Displacement at this end is x1, displacement at this end is x2. We are writing in terms of M1, therefore K2 multiplied by x1 minus x2. Here, the friction is between floor and the mass M1. Therefore, one end is fixed in this case. Therefore, plus Fv1 d upon dt of x1. That's all. But for Fv3, between M1 and M3, the displacement in M1 is x1, displacement in M3 is x3. Therefore, d upon dt of x1 minus x3. How many forces? 1, 2, 3, 4, 5. That's all. Equal to 0. Therefore, no applied force. No applied force. Similarly, if you write for M2, M2 d square x2 by dt square plus because of K2 x2 minus x1 because of Fv2 d upon dt of x2 plus because of fv4 d upon dt of x2 minus x3. How many forces? Because of m1, 2, 3, 4. That's all. 4 reaction forces. 1, 2, 3, 4. Applied force is f of t. That's all. Then for m3 d square x3 by dt square plus no spring, only dashpot. Dashpots are fv3 and fv4. That's all. Therefore, no applied force. So fv3 d upon dt of x3 minus x1 plus fv4 x3 minus x2 equal to 0. No applied force. Only 3 reaction forces. Only 3 reaction forces. Now we got the mathematical model of given mechanical system in time domain. That's all. These 3 equations together represent the given mechanical system. I took this sum because of 2 reasons. One is to explain FE1, FE2, FV3, and FE4. Frictional coefficients can be taken as dashpot coefficients. That is one thing. Another thing is here the electrical system will get some difficulties in uptake. That's why that we'll see now. How to convert this into force voltage analogy. For that, what we have to do is we have to take L1 force voltage analogy. L1 d square q1 upon dt square plus k equal to what? 1 by c1 q1 plus 1 by c2, 1 upon c2 q1 minus q2 plus fv1. fv1 is b. B should be taken as r v1 or r1 simply r1 dq1 upon dt plus r3 d upon dt of q1 minus q3 equal to 0. For second equation, L2 d square q2 upon dt square plus k2 1 by c2. 1 by c2 already we written in the previous equation. We have to reverse that. q2 minus q1 plus fv2. fv2 is r2 dq2 by dt plus fv4 is what? r4 d upon dt of q2 minus q3 equal to v of t, applied voltage. Here we can write for third equation L3 d square q3 upon dt square plus FV3 is R3 d upon dt of q3 minus q1 plus R4 R4 already we wrote. We have reversed that. Q2 minus, sorry, Q3 minus Q2 d upon dt of Q3 minus Q2 equal to 0. Now we can write all these equations in terms of current. We wrote in terms of charge. We know that I equal to dq by dt. Replace in terms of current. What you will get? The first equation is L1 d square, sorry, di1 by dt plus 1 by C1. Q equal to what? I equal to dq by dt. Therefore, Q equal to integral of I dt. Therefore, 1 by C1 integral of I1 dt plus 1 upon C2 Q1 minus Q2. Therefore, 1 upon C2 I1 minus I2 dt. I1 minus I2 dt. R1 dq by d is I1. Therefore, plus R1 I1 plus R3 I1 minus I3. R3 I1 minus I3 equal to 0. 1, 2, 3, 4, 5. This is first electrical equation. For second, L2 di2 upon dt plus 1 upon C2 I2 minus I1 dt plus R2 I2 plus R4 I2 minus I3 R4 I2 minus I3 equal to V of t. This is second equation. Third equation, L3 di3 by dt plus R3 I3 minus I1 plus R4 I3 minus I2 equal to 0. Only 3 forces acting on it. This is third equation. Now we have to draw the equation. You see that in the first equation, I1 minus I2. Therefore, first loop and second loop are adjacent. First loop and second loop are adjacent. In the same first equation, one more I1 minus I3. Therefore, first loop and third loop also is adjacent. First loop and third loop also adjacent. Here, I1 minus I2, first loop and second loop. I2 minus I3, second loop and third loop also adjacent. Second loop and third loop also adjacent. First and third, second and third. Here, I3 minus I1. First loop, third loop and first loop are adjacent. I3 minus I2. Second loop and first loop are adjacent. But anyhow, if you see that first loop and the second loop are adjacent, no problem. That is already we have seen such type. This is I1. This is I2. No problem. I1 minus I2 automatically you will get. We need I1 minus I3. Therefore, it should be adjacent to first loop as well as second loop. Here you will get I1 minus I3. Here Here what you will get? I3 minus I2, I3 minus I2, I3 minus I2, I3 minus, here you will get I3 minus I1 or I1 minus I3. Here I2 minus I3 you will get. So this is the problem. If you take the loop like this, you can finish. This is the crucial point. That's why I took this sum. So L1 is in the first loop only. Therefore, we can draw L1 here in the first loop only. R3 is between I1 and I3. R3 is here. C1 is in I1 only. C1 is in I1 only. C2 is between I1 and I2. C2 is between I1 and I2. R1 is in I1 only. R1 is in I1 only. We can put here. R1 is in I1 only. 1, 2, 3, 4, 5. That's all. If you take second loop, L2 is in I2 only. So we can draw L2 here. C2 is between, already we have drawn, C2 is between I1 and I2. R2 is in I2 only. R4 is between I2 and I3. Therefore, R4 must be here. How many? 1, 2, 3, 4 elements. Yes, 4 elements are there. We can finish. But one thing is pending, that is V of t. That is in this loop only. So V of t is applied here. V of t. So the capacitor, I have to remove this. Some line is there. Be careful. Okay. This is capacitor, remarked. So you can mind those things. L3 is in third loop only. L3 is in third loop only. We can draw here L3. R3 is between third loop and first loop, already drawn. R4 is between second loop and third loop. That's all. That's all. This is electrical analogous of given mechanical system. Force voltage analogy. Do it yourself. Force current analogy. Assignment number question 1 is find the current analogy. The solenoid shown in figure. The solenoid shown in figure produces a magnetic force proportional to current. Proportional to current. Proportional to the current I in the coil. F is the coil. F is the coil. This is the coil solenoid F. In that a force is produced. You know that if you wind a coil and supply current, it becomes electromagnet. If you put any iron outside that coil, parallel to that, like this. If you put any iron here, it will move inside automatically because of a force developed. Force developed by this coil, it will move. This iron will move inside. Permeability, less 800 times less than the air. That's why this iron will move inside. A force is developed. That is sufficient. The force developed in the coil is equal to Ki1. This is instead of applying a force at this end, we can say that a force F of t is applied at this end. We can say instead the coil is given. That's all. So a current is applied I of t. Sorry, a voltage is applied E of t. Because of that, there is a current in the coil I of t. So a force is developed in the coil. That force is F of t. The coil has an inductance of L, resistance R. This is property of the coil. The coil develops a force F. The coil takes a voltage of E of t. The current through the coil is I of t. The inductance of the coil is L. The resistance of the coil is R. The force developed is F. The force is equal to K1 times I. K1 times I, where I is the current through the coil. That's all. Instead of giving simply force, it is given like this to make you confused. In addition that, it has some mechanical property also. This coil has a weight of M1. The coil has a mass M1. The coil has another property because this coil is, the other end of the coil is attached to the fixed surface through B1. Dashpot constant B1. These are the two properties. This beam is, the length of the beam is L1 plus L2. At this point, the beam is hinged. You know what is meant by hinged? Hinged means the door is hinged. One end is hinged. That's why you can move this door. Like that, this beam is hinged at this point. That's why it can move up and down, depends upon the force. This end also moves up and down. About this point O, about this point O, the other end is fixed to mass M2. The other end is fixed to mass M2. The mass has the property of spring K2 and dashpot constant B2. Now, what is the direction of displacement that we have to see? If we see that because of the force developed by this coil, the displacement at this end A is x1. At this end B is definitely, if A comes down means B will go up. B will go up. Therefore, the force developed by M2, K2, B2 are downward. Why? Because X2 upward. X2 is upward. Therefore, the force developed by M2, K2, B2 are downwards. Here, the applied force is F, that is downward. That's why displacement is downward. Therefore, reaction forces developed by M1 and B1 are upward. M1 is upward because of B1 also upward. M2 is downward here, this end. But anyhow, the reaction forces are try to rotate the beam in the clockwise direction. Am I correct or not? The reaction force M1, B1, FM2, FK2, FB2, all the 5 reaction forces try to rotate the beam in the clockwise direction. But the force F try to rotate the beam in the anti-clockwise direction. Am I correct or not? Therefore, if we take moment, clockwise moment and anti-clockwise moment are equal. Therefore, I can say that F1, L1, this is what? Clockwise moment or anti-clockwise? Anti-clockwise moment. Anti-clockwise moment is F1, L1. Force developed at this end. Therefore, F1, L1 is the anti-clockwise moment. That must be equal to all reactional forces. All reactional forces, they try to rotate in the clockwise direction multiplied by distance where it is applied. But some forces are applied at a distance x1, L1. Some forces, some reaction forces applied at a created at a distance L2. Some reaction forces created at a distance L1, some reaction forces created at a distance L2. Therefore, we can write F reaction forces 1 multiplied by L1 plus F reaction force 2 multiplied by L2. Two forces. Two forces, reaction forces. If you convert this into moment, means we have to force multiplied by distance. Anti-clockwise movement, y F1 L1. The force is at this end at a distance of L1. The moment equal to F1 L1. Anti-clockwise. Clockwise moment developed this end as well as that end. This end because of M1 and B1. That should be multiplied by L1. This end M2, B2, K2, that should be multiplied by L2. That's all. That's all about the mathematical model. So what is the mathematical model? The first equation is F equal to K1. Already it is given, but anyhow, it is also part of mathematical model. Second one is F1 L1. F1 L1 equal to F1 L1 equal to the clockwise moment developed this side are M1 d square x1 by dt square multiplied by L1 plus another force V1 dx1 by dt multiplied by L1. Therefore, we can write multiplied by L1 plus in this end, what are the reaction forces developed? Because of M2, therefore, M2 d square x2 by dt square multiplied by L2 plus V2 dx2 by dt L2 multiplied by L2 plus K2 x2 all should be multiplied by L2. That's all. So what you got? So F of t L1 equal to M2 d square x2 by dt square plus K2 x2 plus B2 dx2 by dt multiplied by L2 plus B1 dx1 by dt plus M1 d square x1 by dt square multiplied by L1. I wrote the first second. That's all. If you equate these two moments, you got this equation. You got this equation. Now divide on both sides by L1. So this L1 getting cancelled. Divide on both sides by L1. L1 getting cancelled. But we know that the displacement is very small. This is the distance L1, this is L2. The displacement is x1. Here the displacement is x2. You consider these two are similar triangles. Because displacement is very small, not arc. Very small displacement, x1 and x2. That's why we can take, it is similar triangles. Sides are L1. Base is x1, x2. Therefore, we can say that L1 by x1, L1 upon x1 equal to L2 upon x2. But I want to obtain the mathematical model. Write the differential equation. That's all. Mathematical model is over. We wrote the differential equation. Time domain mathematical model is over. But the second part of the question is, hence determine the transfer function x2 of s upon e of s. But x1 should not be there. to find this transfer function, x1 is another variable. X1 must not be there. That's why we found this relation. Wherever you find x1, that can be replaced by L1 upon x1 equal to L2 upon x2. Therefore, x1 equal to L1 upon L2 multiplied by x2. X1 equal, from this we can write x1 equal to L1 upon L2 multiplied by x2. Now we can write this equation. Now we can write this equation, can be written as f of t equal to L2 upon L1 m2 d square x2 upon dt square plus b2 dx2 upon dt plus k2 x2 plus, we can replace x1 by L1 by L2. Therefore, here also we will get L1 upon L2. Here, this is b1 dx1. We want to write dx2 in terms of x2. Therefore, L1, this constant came out. There is no differentiation for constant. x2, if we differentiate x2, dx2 upon dt, b1 multiplied by b1 plus m1 d square x2 upon dt square. So the entire equation in terms of x2. Now the entire equation is in terms of x2. Now we can take Laplace transform assuming zero initial conditions. Now we can find. Now we can find this equation can be written as, take Laplace transform on both sides, f of s assuming zero initial conditions. F of s equal to L2 upon L1 m2 s square x2 of s plus b2 s x2 of s plus k2 x of s x2 of s plus L1 upon L2. If we take Laplace transform of this, what you will get? B1 s x2 of s plus m1 s square x2 of s. That's all. So now you can bring x2 of s one side. What is the transfer function required? Laplace transform of output upon input. Input is E of s. But here it is in terms of f of s. So now take this. What is the relation for f of s? We have to take E of s. We have to take, that is E of s equal to, we write Laplace transform. Let it be A. E of s equal to L s I of s plus R I of s. That is equal to L s plus R multiplied by I of s. Let it be B. Here, if you take Laplace transform, you will get f of s equal to k1 I of s. From here, you can substitute I of s. From B, you can substitute I of s from B. I of s from B equal to what? E of s upon L s plus R. Therefore, f of s equal to k1. I of s equal to what? E of s upon L s plus R. This is D, equation D. Substitute D in A. F of s can be replaced by K1. Now I am simply replacing here. F of s can be replaced by F of s can be replaced by K1 E of s upon Ls plus R. So find x of s upon E of s, because E of s is the input. You see the diagram. What is input here? Input to the system is E of s. The output is x of x2. X2 is the output. That's why Laplace transform of output upon Laplace transform of input that we have to find. The transfer function model we have to find. So here, if you come here, x2 of s is available, the right hand side. E of s is available, the left hand side. What we have to find? Output by input. Therefore, x2 of s upon E of s equal to, this will come down. This also will come down. Therefore, what you will get is E of s K1 upon Ls plus R multiplied by L2 upon L1 M2 S square plus B2 S plus K2 plus L1 upon L2 Bs plus M1 S square whole bracket. That's all. This is the transfer function of given mechanical system, assuming that x2 is output, E is input. That's all. X2 is output, E is input. Applied voltage is the input. This is the transfer function model of given mechanical system. Transfer function model of given mechanical system. Mathematical. In the next class, we'll see mathematical modeling of armature controlled DC motor and block diagram. That we'll see in the next class.